Well, I'll let you guys put your initials beside your name. It's just kind of a quick way to take a roll. And here is your first example or the first exposure of recursion. Okay? And recursion typically would not be a topic to talk about until much, much, much later in any other type of cisp300 type classes. But I want to put it early. Do you know why? Well, I'm crazy, yes, but the other thing is, if someone claims to understand the mechanism of invoking a subroutine and coming back from a subroutine, but could not follow recursion, that someone did not actually understand the concept of calling and returning, because the concept does not change at all. Whether you're calling a subroutine from itself or calling the subroutine from somewhere else. Are we doing okay so far with subroutine calling and subroutine returning? Okay. But that's kind of strange. Okay. I think this. Someone mentioned that this kind of has the feel of a loop, right? And it does, okay? And it does, have a feel of a loop. There are some languages, weird programming language out there, they do not have loops. Lisp, L-I-S-P, is one of those programming languages where it does not have loops at all. So when you need to do something repetitively, you have to rely on, guess what? Recursion. Okay, it's done by recursion. Okay. Now recursion has a lot of interesting properties. And I picked this example using factorial because factorial has a recursive definition. Okay, let's first take a look at recursion. Look at factorial. N factorial is usually defined as n times n minus 1 times n minus 2 times blah 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 all the way down to 1. Are you guys familiar with the definition of factorial? Somewhat. Okay. So what does that have anything to do with recursion or recursive definitions? Well, let's look at n minus 1 times n minus 2 times blah, 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 all the way down to n. Isn't that really just n minus 1, the whole thing, factorial? I mean, it really is. So that
it
means,
has to be since it's the definition.
Right. So that means if I want to define n factorial, now I have a more elegant way to define n factorial. I can define 0 factorial is 1. Then I can define n factorial is n times n minus 1 factorial. Okay? For n that is greater than 0. And that's it. That's how I can define, n factorial. It is a recursive definition because in order to define what is n factorial, I rely on the factorial of n minus 1. Okay? That means, that means one thing has a structure that is defined by itself. Do we have anything like that in nature we do have something like that too, but when you're using a computer, do we have constructs like that? A particular type of thing is defined by items that are just like the thing that you are defining, except it may be smaller, lower level, just different in some way. What would that be? Folders. Okay, when you look at folders, it also has a similar type of feel. Okay, let me just go ahead and show you, folders. I mean, you guys know folders already. Okay, and we'll look at it from a different point of view. We'll look at it from a list. Okay, this is good. Okay, we just have to pick a folder that has a lot of subfolders, like users. So users here is a subfolder. It's a folder, right? But what can you contain inside a folder? Subfolders, right? So in this case, users as a folder contains a whole bunch of, subfolders. What do we have in one of these subfolders?
More folders.
Even more folders. Okay? What's inside one of these folders? Even more folders. Even more folders. Even more folders. Even more folders. And so on. As I said, this class is really boring because we're doing the same thing again and again. Okay? Do you guys see the similarity, or at least the relationship between what I'm showing here and also the definition of factorial? Sort of. Okay? This is what we call a self-similar structure. Okay? And in nature, we have something like that too. If you look at a tree, okay, just like the trees that we have outside of this classroom, and you look at how a branch can branch off into smaller branches, it's almost the same thing. The main trunk of a tree goes up. At a certain point, it branches out. What if you follow one of those branches? What do you find?
Branches out again.
Smaller branches, but nonetheless branches, right? So this keeps going on until when you get to the very end, then you find a leaf. Okay? Okay? But that's almost the same concept. You define a certain type of construct or structure with self-similar things. And factorial is one of those things. Do we have any questions at this point about subroutines? How to invoke a subroutine, and what do you do at the end of a subroutine? No questions? Any questions about factorial, this particular subroutine that we are talking about? Yep.
When you're dealing with subroutines, is there any limit to the number of times you can recurse through it?
Yes, there is a limit because it depends on how many columns do we have. That's a good question. Let me repeat that question so everybody can hear your question. The question is, do we have any limitations as to how many times you can call a subroutine to itself again and again? And the answer is yes, we do have a limitation, because we can see that every time this subroutine calls itself, it consumes one additional column. In other words, if you only have 500 columns to begin with, then you can only recur, or you can only call recursively up to 500 times. Then you run out of columns. So that can happen. Yes. So there is a limitation as to how many times you can do this, because each time you call the subroutine again, you're not freeing the column from the previous one yet. So you're consuming a new column every time you call yourself, and as a result, you can potentially run out of columns. Are there any other questions about this example? No questions? What do you think these columns correspond to when you take another class like cisp300?
Memory address.
Memory, exactly. Memory locations. Okay? So that means recursive subroutines do use up more resources as you go deeper and deeper into the subroutine. Okay? Any other questions about recursion? No questions about recursion. So you guys are now experts of recursive subroutines. Well, let's use another example. Let's use another example as recursive subroutines. Remember what I said? Subroutines that are recursive are really no different from than pseudocode that do not have recursive subroutines, but subroutines nonetheless. Let's take a look at binary search. Do you guys still vaguely remember binary search? I certainly hope so, because your homework assignment is based on binary search. So we'll go ahead and take a look at binary search, but in a recursive way. Oh, can we look at binary search in a recursive way? Okay. It's actually easy. Okay, it's actually easier than we think it is. Okay, so we say define sub binary search. Okay, so we are turning the binary search algorithm into a recursive subroutine. And this is only going to implement whatever is inside the repeat until, inside the loop itself. So the first thing we want to do is to calculate what is m. Same as before, m is the floor of b plus e divided by 2. And then what we do is we compare an element in the array, A bracket M, and we say, is that less than a value that we are looking for K? Okay, same stuff that we were dealing with in your current homework assignment. If that is not the case, we want to see if K itself is less than the element in the array that we are looking at. And if, okay. What do we put here? In other words, if this is true, if A bracket M is less than K, have we located the item that we are looking for? No. So that means that we have to invoke the subroutine again, because the subroutine is supposed to find out or figure out whether the value we are looking for is there or not. Okay. So we'll say invoke binary search. Now this program is not complete by any means, but I'm just pointing out the structure of the program right here by saying that yes, this is a recursive subroutine, because when I cannot find the item that I'm looking for, I will invoke the subroutine again to perform the same algorithm again. Except before line 4, I need to do something else. And before this line, I also have to do something else. Don't I need to do like something about B and E?
Change the value.
Okay, in this case, B gets M plus 1. In this case, E gets M minus 1. Okay. Like that. And there's one more thing I also have to do. Basically, I have to insert a new line here and insert a new row here. I only do this if I already know that B is still greater than or equal to E. Because if B is already less than E, what do I know?
You're out of
Oh, excuse me, I take it back. This is the other way around. B has to be less than or equal to E. If B is greater than E, what do I know?
You had to end. You had to search through everything.
Yep, that's right. So, okay, I have to adjust the indentations here a little bit. And indentation really is important in this case because I have a conditional statement inside another conditional statement. Okay. And because the entire thing is inside the subroutine, I have to indent just one more time, like that. That's binary search in a recursive way. So let's go ahead and track this one down and see how it works. Okay, we'll only use a simple example because I don't want to use up too many columns, because this one will use up columns. We'll go ahead and say B has to be initialized to 0. The initialization is now outside of the subroutine because we cannot initialize B and E again and again. And E is the number of elements in A minus 1. And then we say invoke binary search. And then we can say, let's make a conclusion found is, whether A bracket M equals to the value we are looking for or not. Give these guys line numbers, just like that. Okay, so here is an algorithm that we should be familiar with at this point, but it's turned into something that is not repetitive. Okay, it is now a subroutine and it is recursive. We'll go ahead and trace this algorithm. We have, enough time to do it. Yes, we do. It all depends on how big I make the array, right? If I give you an array of one element, then I can be done like in no time. But that would not be very fun, though. Okay, we got comments. Oh, I missed one.